Hi, welcome to the Messinger Lab here at the City College of New York, Chemical Engineering Department. My name is Colleen. I'm a second year PhD student, and today I will teach you the basics of NMR. Hey guys, it's Colleen in voiceover form. So what I'm showing you guys right now is me packing the 1.6 millimeter solid state rotor. Our group does both liquid and solid state, but I wanted to show you guys solid state today because I think it's a little more interesting. There's more parts to it. While I'm showing you this, I'm also going to explain a little bit of the physics background behind NMR. So NMR is one of the many methods that chemists and chemical engineers use to find out what's in their samples. It records the relaxation behavior of spins in specific nuclei after a magnetic field pulse is applied. So if that sentence was a little confusing or didn't make sense at all, don't worry, because I'm going to explain it a little further. So all elementary particles like protons, neutrons, and electrons in an atom have spins. There's no macroscopic version of a nuclear spin, and because of this, our language doesn't have the words to describe what a spin is. So what I can tell you about a spin is that they're forms of angular momentum, which means that they are vectors. These particles also possess nuclear magnetism, which is not to be confused with bulk magnetism or macroscopic magnetism, which is what you guys would probably think of when you think magnetism. It basically just means that they're able to interact with a magnetic field. So if you apply a magnetic field to them, then they will change direction. So this is me showing you guys one of the spectrometers in CUNY's ASRC. We share it with a couple other groups, and this is our probe that we got from Phoenix NMR, and right now I'm changing the probe head. So the probe basically houses the sample when it's in the spectrometer, and the spectrometer is kind of like a giant magnet, and whenever the magnetic field of the magnet is turned on, then the spins either align or they go against the magnet's magnetic field. And then they undergo an RF pulse, which switches the magnetic field into like a perpendicular direction. And when the pulse is turned off, they relax back to the original magnetic field. And based on how they relax, we get a graph in frequency over time. And then we can use that to Fourier transform it and get chemical shift, or intensity as a function of chemical shift. And the chemical shifts are what we use to determine what's actually in the sample, to determine the functional groups of our sample. So here's me tuning, and yeah, that's about it. Hi, thank you for watching, guys, and if you have any questions, feel free to reach out to me, and yeah, okay, bye.